For the last few years, artificial intelligence has completely mastered language. It generates stunning images, it writes complex code in a matter of seconds. When it's confined to a screen, it honestly feels unstoppable. But here's the thing. Take that exact same intelligence, put it inside a physical machine, and ask it to navigate the real world. Suddenly, everything breaks down. Welcome to This Explainer. Today, we're looking at why moving AI off our screens and into physical reality is such a monumental, incredibly difficult challenge.
The sheer scale of this challenge really comes down to one simple thing: the cost of failure. Think about it. A chatbot operates in a purely digital realm. If it makes a mistake or hallucinates a completely made-up fact, what happens? You just hit refresh. The cost of failure is literally zero. But a physical robot, if it makes a mistake, it breaks something. It damages expensive equipment, it wastes materials, or far worse, it could actually hurt someone. We are moving from a world of minor digital inconvenience into a world of real-world, high-stakes consequences.
Okay, let's dive into this because the fundamental difference here is pretty profound. Language is incredibly flexible. You can misspell a word or completely scramble a sentence, and a human, or an AI for that matter, can still figure out what you meant. A language model absolutely thrives in that kind of flexibility. But the physical world, it does not negotiate. Gravity, friction, momentum, solid objects, these are absolute. There's no gray area. AI now has to learn to abide by the deeply unforgiving laws of physics. And that brings us to what we call physical AI. So what is it? Basically, these are AI systems designed to sense and actually act in the real world. We're talking about robots, drones, autonomous vehicles, and advanced sensor networks. And look, this isn't just theoretical sci-fi anymore. In fact, physical AI is currently ranked by Gartner as one of the absolute top strategic technology trends for 2026 and the coming decade. It is, without a doubt, the next major frontier of technological evolution. So why does this matter to you and me right now? Well, AI is officially leaving the screen to manage the critical physical systems all around us. We are witnessing a massive push to integrate autonomous systems into things like factory automation, warehouse logistics, and even hospital care. And soon, this is going to extend right into our smart homes and connected city infrastructure. Solving physical AI will literally transform our entire economy, but getting to that point requires overcoming some immense, completely unseen hurdles. Now, what's really interesting about this slide is how it perfectly frames the problem. Think of a standard chatbot as a highly intelligent person sitting at a desk in a perfectly quiet, empty room, just answering written questions. It's a highly controlled, predictable environment. Physical AI, on the other hand, is like taking that exact same person, putting a slight blindfold on them, and asking them to walk through a crowded, messy, noisy workshop. They have to hold fragile objects, step around moving people, and navigate totally unexpected obstacles. The level of real-time awareness required is exponentially higher. To even survive in that messy workshop, a robot has to rely on a massive, totally invisible infrastructure. It's not just running one piece of software. It needs a web of cameras and LiDAR sensors just to see its surroundings. It needs real-time perception to constantly update a complex 3D world model inside its digital brain. It then has to feed all of that data into complex planning systems, which finally trigger physical actuators and motors. And wrapping around this entire system are incredibly strict safety layers and constant human supervision. Let's walk through what actually happens under the hood. Every single time a robot interacts with its environment, it carries a massively heavy computational burden. In mere fractions of a second, it has to sense the environment, understand the objects in front of it, decide on the safest possible action, command its motors with absolute precision, and then, crucially, use feedback loops to check if that action actually worked. This exhausting cycle loops continuously, thousands upon thousands of times every single minute. Because this computational cycle is so intense, industrial robotics currently only really succeeds in highly structured environments. Think of your standard, predictable factory cells, where the lighting is always exactly the same and the motions are perfectly repetitive. But the future we're aiming for demands unstructured environments. We want service robots that can navigate messy living rooms, busy hospital corridors, and totally unpredictable city streets. Taking a machine out of a perfectly structured factory and putting it into an unstructured public space is arguably the greatest engineering hurdle of our time. Inside those unstructured environments, we immediately hit a massive bottleneck: dexterity. Look, an AI can generate a brilliant 1,000-word essay in a matter of seconds. But programming a robotic hand to simply pick up a soft object, like an egg, without either crushing it or dropping it, that is incredibly difficult.
Predicting text is essentially just math and pattern recognition. But adjusting physical grip strength to account for material slipping in real time, that requires a level of physical intelligence that we are still really struggling to perfect.
So the crucial point is that this core bottleneck really comes down to sheer economic reality. Training large language models relies on digital text. That data is cheap, and it can be easily scraped from the internet by the billions. But training physical AI, that requires real-world hardware. Robot data is staggeringly expensive to collect. You actually need physical machines running slow, repetitive trials just to gather data on how different objects feel and behave. You cannot simply scrape physical experience from the web. You literally have to generate it, one physical interaction at a time.
Now, engineers obviously try to bypass this slow process using digital simulations, essentially creating hyper-realistic virtual worlds to train the AI. But here's the catch. Simulation has hard limits. The real world is incredibly messy. A simulation really struggles to capture things like unexpected friction differences on a dirty floor. It fails when there are sudden lighting changes, endless variations in the shape of objects, degrading hardware sensors, or perhaps the biggest wild card, unpredictable human behavior. That gap between a perfect simulation and messy reality is exactly where physical AI often fails. And because of that gap, safety and governance suddenly become the ultimate priority. Think about it. When a digital algorithm recommends a bad movie, it's annoying. But when an algorithm that's steering a heavy autonomous machine miscalculates, it can be lethal. The extreme risks associated with failing in unseen environments mean that widespread adoption is going to require bulletproof reliability. We have to establish deep societal trust before we can ever let these machines freely share our physical spaces.
Let's move to this timeline and see how this builds out over the coming years. Because of these high stakes, we are definitely not jumping straight to humanoid robots cooking us dinner tomorrow. The timeline is progressing cautiously, step by step. First, we mastered fixed factory cells. Right now, we're mastering structured, autonomous warehouses. The next frontier is slowly moving into unstructured public spaces. Think delivery bots on sidewalks. Only after we conquer that, years down the line, will we finally reach general-purpose robots roaming around inside our highly unpredictable homes.
To eventually reach that final stage, several massive breakthroughs have to happen simultaneously. We're going to need the deployment of much better, cheaper sensors. We need advanced real-world simulations that can perfectly mirror reality. Hardware costs have got to plummet to allow for a massive expansion in physical training data. We need safer control systems. And most importantly, what changes next is that we will see narrow, task-specific deployments first. We'll build machines designed to do just one physical thing perfectly, long before we ever achieve any sort of general physical intelligence. The chatbots and digital assistants we interact with today are absolutely incredible achievements. But generating language? That was only the first step. The profound leap from digital words to real, physical action is the true frontier of our time. The future of AI isn't just going to be measured by what it can say to us on a screen, it will be measured by what it can safely do right next to us. So the question is, when these physical machines finally step out of the factory and into your living room, how much of your physical world will you trust them to control?